Hello, it's me, Biomic, and these are my group members. I'll play the video of the animation. In this scene, we begin with a single astronaut who is walking on the moon's surface, and then from his side pocket, he grabs his family photo as he misses his family. Then the camera cuts to a close-up scene by GLTF camera, putting the audience close to the character's moment. After the close-up camera, a rocket launches and takes off to unknown journey in the space. And as the camera moves back and outward, it exposes planets and the sun. In the next slide, I will demonstrate how the visual composition supports the story by dividing items into forefront, middle ground, and background levels. So in the front, we have the moon sphere and props grounded, grouped as Moore Children group. This grouping allows us to move and scale these elements as one unit for consistent framing throughout the scene. The items in the mid-ground, such as the ice monolith and boulders, are tuned slightly bigger to draw eye outward. The solar system serves as the background, with planets having calculated orbits and sun placed behind the plane to provide dramatic direct light and extended shadows. This layered strategy keeps the viewer emotionally engaged within the snapshot moment. By keeping the structure in mind, the scene's storytelling is based on a small number of items and people. First is an astronaut, who is a character created as a GLTF model with a family photo attached to his side torso. Then the one-shot animation and camera scene enable an intimate close-up. Next is an interactable reflective box that invites the player to push E button. It uses a cube camera to create real-time reflections. Rocket is a cinematic prop near the horizon, and it launches across the animation with an accelerating velocity, controlling the timing of the zoom out. Ice monolith is a transmissive refractive element that captures light and creates a subtle focal point in the middle ground. Planets and Sun are modular planet nodes in orbit, offer an enormous scale as the camera pulls back, while the bloom on the Sun shows the cinematic. Next, we will look at how the interaction starts the cinematic. Now I'll pass to Icarus.
So thanks for talking about the um, story and then also show a demo. And then I'm Icarus. I will talk about the interactive flow of our WebGL project. So in this project, user will be able to control an astronaut to walk on the moon, and then we made it interactive for the user to use the astronaut to walk around the moon, so that the user would gain an interactive experience by controlling the astronaut. So the key step for the um, whole project is the user will be able to control the astronaut as being said, and then they will use the astronaut to approach to a certain cube, and then that cube has a distance check variable. If the astronaut is near the cube enough, a prompt will appear and then ask the user to press E. After pressing E, uh, as being shown in the demo, an animation will show up, and then the user will be able to watch the animation. Note that the inputs are restricted during the animation to avoid interruption. And then for the animation part, we decide to make it into two approach. The first one is we decide to make the animation for the astronaut uh, like body action and then body language by using Blender. And then the second one is directly uh, animate some object inside WebGL. So for the Blender part, we did use Blender to rig the astronaut and then animate it by using Blender's animation pipeline, which is the keyframe. So what it does is we first insert a keyframe for a certain um, like posture, and then we insert another keyframe in a certain time spot again, but with a different posture, so that the computer will automatically interpolate the middle action for us. So that, as you can see in the demo, the astronaut is being able to walk to pick up the photo and then look into the space. That is achieved by using the keyframe method mentioned before in Blender. And then for the second one, the WebGL approach, as mentioned here, uh, with this we did some animation in WebGL, which is the rocket launch, uh, also the planet spinning around the Earth. That is also achieved by using WebGL primitive animation method. So for the rocket launch, uh, it is able to achieve the procedural lift because the rocket velocity is increasing each frame. And then for the camera zoom in and out, uh, we did it. We achieved it by increasing the distance. Um, sorry, we achieved it by the speed increases with distance to create a semantic acceleration. And then for the planet spinning around the Earth, we adjust the orbit angle like cosine or sine per frame to achieve the spinning animation. Uh, I will now pass the time to Ken to talk about the visual.
Let's move on to our visual and rendering part. Here I have three key points. First is our apply a physical based rendering material for our eyes object. You can see in the second image, the eye surface reflect the foreground scenes. Also, it will see some background scene in the eye surface. Next, we apply different effects for our scenario. First, you can see the sun have a bomb effect in the sun image. You can see the border of the sun have a little bit brightness. Also, we have a depth of the field. You can only see clearly on the focus point object. If not in the focus point, other thing will little bit blur. Also, you can see have a shadow effect. You can see in the last image, it have a big shadow for our eyes object. In the cube box, reflection for a button. You can see in our Earth have a some part is light have a light and some part is have a shadow. The mirror cube box will reflect the scenes. Last thing, we apply the particle system for the rocket fire and the solar flares. Let's move on to performance and synchronization. Here I have four different key points. First, to reduce the GG charm, we choose to reuse the vector and a particle instance for example, the fire and the sun flare. Second, we keep the animation and stay flat to avoid race condition. For example, we actually know we have two different animation. One for the idle, second for the walking. We in one time it can only apply one animation. Next, we optimize the post process by downsampling past and animation instance smoothly. For some example, the shadow need to sampling the map size. We adjust the map size to reduce the computational requirement. At last, we ensure that the transform update order is in parent before the child. For some example, in the workhead, the fire will the child of the workhead. When the workhead moving, the fire also follow the workhead. That's the end of our presentation. Thank you.